Imagine a world where you could walk from what would become America to Africa, Europe, and Asia, all without crossing an ocean. It might seem impossible, but it happened. Millions of years ago, all the continents were united into one enormous landmass. And if you stood in the very center of that supercontinent, as strange as it sounds, I believe you'd find a scorching desert stretching as far as the eye could see. I want to take you back to that time, 300 million years ago, when our planet looked utterly different. This was the era of Pangea, a supercontinent surrounded by a single vast ocean called Pantalus. All the land masses were joined together. It was German meteorologist Alfred Wegener who first truly pieced this puzzle together. His book, The Origin of Continents, published in 1912, laid out the remarkable idea that the continents we know today were once part of a single immense landmass. This was more than just a theory. It was a turning point. Wegener's concept suggested a dynamic Earth, one where continents moved and interacted in ways we hadn't previously imagined. Later, in 1920, Erich von Degner refined this idea, naming it Carboniferous Pangea, linking it to a specific period with unique climatic and biological conditions. It placed this vast, unified landmass at the center of a new understanding of our planet's history. Wegener didn't just dream this up, though. He had compelling evidence. He noticed, for instance, how the continents seemed to fit together like pieces of a giant puzzle. The coastlines of Africa and South America, in particular, looked like they were once connected. Then there were the fossils. Identical fossils of ancient species, both land-dwelling and aquatic, have been found on continents now separated by vast oceans. How could aquatic reptiles, for example, possibly cross the Atlantic? The presence of these fossils strongly suggests that the continents were once joined. Even the mountains tell a story. Geologists have found similar rock formations on continents that are now far apart. This indicates that these rocks formed together before the continents separated. The layers within the rocks, the coastal landscapes, these details caught the eyes of scientists who realized it couldn't be mere coincidence. And consider coal. This fuel source typically forms in warm, humid environments, so why is it found under the ice caps of Antarctica? It suggests that Antarctica was once in a much warmer climate, one that allowed for the formation of massive coal deposits. The term Pangea entered scientific vocabulary in November 1926 at a symposium, thanks to the American Association of Petroleum Geologists, marking a major step in the acceptance of Wegener's ideas. Initially, Wegener believed that Pangea broke apart due to centripetal forces from the Earth's rotation. But he couldn't quite explain the mechanism of continental drift, and this led to resistance to his ideas. The idea seemed physically unrealistic at the time. It wasn't until after his death, with the emergence of new data, that his theories gained wider acceptance. In the 1960s, English geologist Arthur Holmes proposed an alternative mechanism: convection in the Earth's mantle. He suggested that these currents could drive plate movement. Exploration of the ocean floor revealed significant features that helped explain seafloor spreading. These discoveries became the foundation for plate tectonics. The theory of plate tectonics replaced the earlier idea of continental drift, explaining not only the existence of Pangea, but also how the continent slowly moved over time, eventually leading to its fragmentation. Modern Pangea formed around 335 million years ago, uniting almost all of the planet's continental landmasses into a single whole. But Pangea wasn't unique. Supercontinents seem to appear in cycles throughout Earth's history. It's quite possible that others existed before Pangea. Scientists have even reconstructed some of these earlier supercontinents using geological data. One notable example is Pangea, which is believed to have formed around 600 million years ago, before breaking up again. There's something awe-inspiring about imagining the Earth's continents shifting across vast stretches of time, colliding and separating in a slow dance that shapes our world. I've spent countless hours tracing the outlines of ancient landmasses, trying to reconstruct the puzzle of our planet's deep past. One of the most fascinating concepts is that of supercontinents, colossal landmasses that have assembled and fragmented over billions of years. Years later, one of these supercontinents would play a key role in the geological cataclysms of that time, especially the changes in ocean currents and climate. Another hypothetical ancient supercontinent is Rodinia, which is believed to have formed about 1 billion years ago during the Proterozoic. Its appearance was important for the geological history of the Earth, as Rodinia became the source of future continents and oceans. Supercontinents that existed about 750 million years ago, including Rodinia, fragmented. This led to serious tectonic and climatic changes such as the snowball Earth hypothesis, which suggests that the planet survived almost complete glaciation. Geological data also indicates the existence of Columbia. The supercontinent Columbia, which likely existed between 1.8 billion and 1 billion years ago, remains a mystery to scientists. However, its existence raises important questions about the supercontinent cycles that shaped the tectonic evolution of our planet. Looking even deeper into the past, researchers have discovered preliminary evidence for the existence of the supercontinent Kenorland, which is believed to have existed between 2.7 and 2.1 billion years ago. This supercontinent and its successors played a key role in the early stages of the Earth's tectonic evolution, and likely contributed to significant climatic and atmospheric changes on the planet. The most ancient of them is Valbra, whose existence is dated to approximately 3.6 billion to 2.5 billion years ago. At the time when the first sections of the Earth's crust began to form, the supercontinent Valbra could have been the starting point in the evolution of supercontinents. It witnessed the first tectonic processes that shaped the shape of our planet. The supercontinent of Gondwana played a key role in the formation of Pangea. It already existed before Pangea was formed, and was created as a result of the merger of several large continental blocks, mainly in the southern hemisphere. Gondwana included the lands that today correspond to South America and Africa, as well as Antarctica, Australia, and the Indian Ocean Peninsula. Even after the breakup of Pangea, which occurred much later, Gondwana remained a single whole for a time. The geological history of the formation of Pangea is explained by the convergence and collision of two large supercontinents, Gondwana and Laurasia. Laurasia was a landmass which included the territories of modern North America, Europe, and parts of Asia before the formation of Pangea. Laurasia, also known as Euramerica, was formed as a result of the collision of the Siberian continent with Laurasia. This tectonic process occurred during the Carboniferous period, approximately 350 million years ago. The creation of Pangea was not a one-time event that occurred in a short period of time. It was the result of a series of successive collisions between separate continental blocks. After Gondwana and Laurasia, other smaller land masses, such as Siberia, came closer to each other. Northern China and southern China gradually joined this vast structure. The final formation of Pangea led to the emergence of a giant tectonic plate, a single continental mass that dominated the Earth's surface about 160 million years ago. During this period, Pangea had a significant impact on the climate, ocean circulation, and the evolution of life on Earth. However, the tectonic forces that led to its formation continued to operate for about 200 million years. Millions of years after its formation, Pangea began to disintegrate. Under the influence of plate tectonics, this process marked the beginning of the formation of the continents we know today. One of the main components of this collapsing Pangea was the land of Gondwana. It existed for another several million years before it split apart to form the continents that extended to modern southern regions. Complex tectonic processes have shaped the geography of continents. One of the key events was the displacement of a small supercontinent, having penetrated far from Gondwana across the ocean that divided the northern hemisphere. This separation of two huge land masses led to the formation of a new ocean, known as the Proto-Tethys Ocean. This event marked the beginning of a series of geological transformations that have significantly changed the appearance of the planet. Soon after, Proto-Laurasia broke up into several parts: continental Laurentia, which is today North America, Siberia, which developed as an independent continent, and Baltica, which became the basis for Eastern Europe. This tectonic rupture not only led to the emergence of new continents but also contributed to the formation of two new oceans, the Iapetus Ocean and the Conti Ocean. Laurentia remained in the west, Baltica formed on the east, and Siberia was located to the northeast of Laurentia. In the Cambrian period, Laurentia, which later became North America, was located in the water zone, washed by three large oceans: the Panthalassic Ocean in the west, the Iapetus Ocean in the south, and the Conti Ocean to the east. This geographic configuration promoted marine biodiversity, with the exception of those life forms that were common on land. Primitive marine life emerged during the Cambrian explosion. However, with the onset of the Ordovician period, conditions began to change, and a significant event occurred: the formation of the geological microcontinent Avalonia, which later became the basis of the northeastern United States. Avalonia separated from Gondwana, uniting New Scotland and part of England. Its movement towards Laurentia marked the end of the Ordovician period. From this moment on, a new stage began in the formation of supercontinents. Baltica collided with Laurentia and soon with Avalonia, which merged with these two land masses. I sometimes imagine the slow, almost imperceptible dance of continents across the Earth's surface. For millions of years, these collisions and drifts have sculpted our planet, influencing everything from ocean currents to the very evolution of life. It's almost incomprehensible to think of the Earth's features as being so fluid, so changeable, over vast stretches of time. The gradual movement of Gondwana was just the opening act. It was the first stage in a much grander play, the formation of Pangea. This process would ultimately lead to a single supercontinent dominating the entire planet. The second act involved a series of complex tectonic collisions, the most significant being the meeting of Gondwana and Europe, and there was also America during the Silurian period. A continental bloc, Baltica, which makes up part of modern Eastern Europe, collided with Laurentia, forming Euramerica. This continental mass was essentially the merger of Laurentia and Baltica. Avalon, a microcenter in the northeast, remained separate, as the remains of the Iapetus Ocean hadn't fully merged. It existed as a narrow sea route between Avalon and Laurentia, showing how slowly these land masses converged. Meanwhile, other tectonic changes were happening in the southern hemisphere. In southern Europe, still part of Gondwana, a fragment, the core of America, began to drift north. It headed towards the continent through the Reich Ocean, newly formed and separating the southern land masses from the northern ones. In the north, during the Devonian period, a small, almost completely flooded plate collided with the southern part of the Baltic, further altering the structure of the continents. At the same time, the Conte Ocean, a brother of the Iapetus Ocean, was shrinking due to the collision of the Siberian island arc with the Baltic Sea. This collision contributed to the close of the ocean in the east, and a new ocean, the Ural Ocean, began to form behind the Siberian island arc. It arose from the convergence of continental plateaus, paving the way for future tectonic collisions that would shape the region. By the end of the Silurian period, North and South China, two separate continental blocks, broke away from Gondwana and began to move north toward a drying ocean. A new ocean, the Paleolithic, gradually opened up to the south, marking an important stage in the development of the primitive lands. During the Devonian era, the Gondwana Plate began its northward journey, gradually closing the Rhaetian Ocean as it approached Euramerica. This movement laid the groundwork for the third and final stage of Pangea's formation, uniting nearly all the land masses on the planet. These repeating collisions, the slow, steady drift of continents, significantly changed the Earth's appearance over millions of years, influencing ocean currents, climate, and the evolution of living species. At the beginning of the Carboniferous period, this tectonic convergence intensified, shaping the modern configuration of continents and mountain ranges. Northwest Africa, then part of Gondwana, collided with the southeastern coast of Eurasia, forming massive lands that included the Laurentian Baltic. This collision led to the formation of the Southern Appalachians, a mountain ridge extending from north to southeast North America, as well as the Cordillera to the plateau in what is now Spain. Around the same time, South America, another fragment of Gondwana, was slowly moving north toward southern Laurentia. Parts of eastern Gondwana, including India, Antarctica, and Australia, began moving toward the South Pole, causing significant climatic changes, including the formation of glaciers. Northern and southern China, separated from Gondwana, existed as continents, freely floating in the ocean, protected by the microcontinent Kazakhstan. In the Carboniferous period, Kazakhstan began to shift and collide with Siberia, becoming half of Siberia itself, which had been an isolated continent. Near the end of the Carboniferous period, another significant tectonic event occurred, the collision of western Kazakhstan with the Baltic. This collision led to the close of the Ural Ocean and the beginning of the formation of the Ural Mountains, a mountain system that still exists today, marking the border between Europe and Asia. The merging of these lands led to the formation of the supercontinents Laurasia, an important component of Pangea. South America continued its northward journey and collided with southern Laurentia, closing the Rake Ocean. The remains of this ocean can still be found in the southern United States. This Silurian collisional era ended with the formation of the southern Appalachians and contributed to the creation of the Ouachita Mountains, a mountain range in the southern states. Meanwhile, Gondwana, near the South Pole, experienced the formation of glaciers across many of its territories: Antarctica, India, Australia, South Africa, and South America. These continents all appeared on Earth at different points in its history. Finally, near the end of the Carboniferous period, the North China Block collided with Siberia, completely closing the Proto-Ocean and marking the disappearance of one of the most ancient oceans. I sometimes imagine the Earth as a giant jigsaw puzzle, constantly shifting and rearranging itself. Once, all the pieces fit together perfectly, forming a supercontinent called Pangea. It's hard to picture now, looking at our familiar world map, but for a vast stretch of geological time, nearly all the world's land was united. Pangea wasn't static. It rotated, changed its orientation, and eventually began to break apart, setting in motion the formation of the continents as we know them. During the Permian period, the Carria Plate broke away from Gondwana and drifted north, opening the Tethys Ocean. This was a period when most of the world's landmass was united into Pangea. Then, during the Triassic period, Pangea rotated slightly, and the Cimmerian Plate continued to move, cutting through the shrinking Paleolithic Ocean. This continued until the middle of the Jurassic period, gradually closing the Paleotropic Ocean from west to east. This process formed mountains, defining the boundaries between the continents. Pangea, at its peak, resembled the letter C, with the vast Tethys Ocean inside, surrounded by land. This unique configuration profoundly affected ocean currents, climate, and biodiversity. The weather on Pangea was vastly different from today's conditions. There were ice ages with huge polar ice caps and warmer interglacial periods when these glaciers melted. During ice ages, water accumulated in glaciers, sometimes dropping sea levels by more than 100 meters. Yet there were also times with no permanent ice at the poles. Temperatures soared, with carbon dioxide levels in the atmosphere 5 to 20 times higher than present. This created a significant greenhouse effect, especially during interglacial periods when sea levels rose. Warm coastal swamps flourished with amphibious insects and reptiles, and shallow seas teemed with marine life. These creatures experience cycles of warm climate, alternating with glacial periods, causing significant sea level fluctuations. As glaciers advanced, the seas retreated, freeing up more land. Conversely, global warming and melting glaciers led to rising sea levels, flooding coastal plains and forcing flora and fauna to migrate. Eventually, the Earth's internal heat began to accumulate under Pangea, leading to land uplift and further sea level increases. These climatic shifts contributed to vast equatorial deserts due to water shortages. These conditions brought high temperatures, strong winds, and frequent dust storms. Instead of two desert belts separated by tropical wetlands, Pangea featured a vast desert region extending to the equatorial zones, disrupting normal atmospheric circulation. These periods occurred in subtropical zones due to atmospheric circulation, specifically Hadley cells. Scientists discovered this while studying rocks and sediments from that time. Evaporates, salt deposits formed by water evaporation, show that the interior of Pangea was extremely arid, with hyper-arid deserts reminiscent of modern Ecuador. The NIPA geological team's discovery of a Middle Permian rock formation in western Kansas provided valuable insights into the extreme climatic conditions of Pangea. This region was a vast desert with temporary salt pan lakes, leaving behind salt deposits like elite. This landscape resembles modern deserts, such as those around Lake Eure in southeastern Australia. Brine trapped in these salt deposits indicates extremely high temperatures, significantly exceeding even those in Death Valley, California until 1973. Later findings suggest more moderate maximum temperatures, around 43 degrees, but still making life difficult due to extreme temperature variations between day and night. These extreme temperature swings were due to the vast continental areas being far from the oceans. Later, in the Cretaceous period, another episode of extreme heat occurred. I sometimes imagine what it must have been like to walk across Pangea, a single supercontinent stretching around the equator, marked by extreme climate conditions that fostered new life. But this world also ended in tragedy. A cataclysm roughly 252 million years ago, the Permian Triassic extinction. It remains the largest extinction event in Earth's history, wiping out nearly 90% of marine species and 70% of terrestrial species. The planet became virtually uninhabitable, transforming Pangea into an arid world. Despite the generally warm climate, a variety of species found ways to survive in the desert. Regional differences, especially in rainfall distribution, played a vital role in shaping the climate. These changes were closely tied to Milankovitch cycles, those periodic vibrations caused by the Earth's rotation and the eccentricity of its orbit. These cycles influenced how much sunlight reached different parts of the planet during the late Triassic period. Regions closer to the equator basked in more sunlight, boosting energy production. Meanwhile, higher latitudes received less sunlight, but experienced more frequent, albeit smaller, amounts of precipitation. Pangea's ecosystems were unique, shaped by geological and climatic conditions that significantly influenced biodiversity and the interactions between species. The formation of this supercontinent led to the emergence of new life forms, but also brought about less frequent rainfall, especially inland due to the distance from the oceans. The formation of Pangea had a profound impact on the evolution of life, affecting both terrestrial and marine ecosystems. As the continents merged, the seacoasts expanded significantly, leading to a reduction in coastal areas, which are typically rich in biodiversity. Coastal marine ecosystems suffered, and marine life redistributed itself towards new niches. Along Pangea's shores, seasonal fluctuations were pronounced, with hot summers and harsh winters, a direct consequence of the continent's enormous size. However, near the Tethys Ocean, the climate was more moderate, with high humidity, creating favorable conditions for forests and fertile lands. The center of the supercontinent, far from the oceans, was a different story. It experienced severe drought, creating a desert climate. This vast distance from moisture sources made large areas unsuitable for many forms of life. However, these dry conditions favored the evolution of amniotes, the ancestors of reptiles, birds, and mammals. Amniotes had a distinct advantage. They could lay eggs on land, away from water, thanks to the amniotic membrane, which protected the embryo from dehydration. This allowed them to explore drier regions inaccessible to amphibians, which needed water for reproduction. The increasing aridity in the western parts of Pangea became a major center for the evolution and diversification of life. Amniotes adapted to these dry conditions, evolving to survive in the harsh climate. This also played a significant role in their geographical expansion as environmental conditions improved. The interior of Pangea, characterized by climatic extremes, influenced the evolution of organisms like the massive herbivorous reptiles, the pariasaurs. Their bones show unique growth patterns that provide clues about how they adapted to their living conditions. During periods of severe environmental stress, likely caused by droughts or extreme heat, dinosaurs in this area could only survive if conditions were just right. These cold-blooded giants depended on the ambient temperature to regulate their body temperature. During the Upper Triassic, the distribution of sediments played a key role in dividing habitats between mammals and reptiles on Pangea. The ancestors of mammals inhabited tropical regions with a monsoon climate, where precipitation fell twice a year, contributing to their development and allowing them to move north. In temperate zones lived procolophanid reptiles, better adapted to conditions with heavy rains only once a year. This difference in rainfall significantly impacted the geographical distribution of both groups. Mammals requiring large amounts of water were naturally limited to regions with abundant precipitation, influencing their very biology. The story of Pangea is a story of both unity and surprising division. I find myself pondering how, despite the absence of oceanic barriers, species distribution wasn't as universal as one might expect. Pangea's amphibians, reptiles, and the earliest dinosaurs freely roamed, creating a single, unique ecosystem. Yet, even within this vast land, ecological niches formed, influenced by climate and the ability of species to adapt. Amphibians, for example, with their process of waste, needed more water, which limited their range compared to reptiles who could thrive in drier conditions. Reptiles found their haven in the temperate zones north of Pangea, avoiding the equatorial regions. The absence of oceans allowed species to spread, with some becoming cosmopolitan, occupying diverse ecological niches across the world. The sheer size of Pangea meant that species with successful adaptations could thrive in many different environments. This led to the discovery of similar plants and animals in regions now separated by vast oceans and land. Plant life on Pangea was fairly homogeneous, influenced by a climate of contrasting conditions. Arid zones saw the rise of coniferous trees, giant ferns, and other drought-resistant species, while humid regions flourished with dense forests. Mass extinction events, especially during the Permian-Triassic and Triassic-Jurassic periods, played a crucial role in shaping Pangea's cosmopolitanism. The Permian-Triassic extinction created an ecological void, allowing resilient species to rapidly spread. Lystrosaurus, a member of the Theropsites group, took advantage of this and populated nearly all of Pangea. It's a classic example of disaster fauna. Low diversity species capable of mass expansion after a crisis. But even in a world ripe for development, archaeological and paleontological evidence suggest that species had limited geographic ranges. This provincialism occurred despite the lack of physical barriers. Climatic differences within Pangea, especially monsoons, played a significant role. Monsoons, with their seasonal winds, created variations between equatorial and polar regions. These climatic shifts, with pronounced seasons and latitudinal differences, rendered some regions inhospitable. Consider the ecological plants of the period, with their primitive seeds. They adapted specifically to the cold conditions of southern Pangea's Gangguan regions. But even without mountains or seas blocking them, these permafrost-adapted species couldn't spread beyond those territories, likely due to the warm, humid climate prevailing in the aquatic zones to the north. This climatic difference maintained a certain ecological isolation between Gangguana species and those from the more diverse northern regions. During the Triassic, theromorphic Permian species from the north eventually dominated Gangguana's ecosystems, possibly due to climate change or local extinctions that displaced native species. The formation of Pangea may have influenced mass extinctions, especially during the Permian and Triassic. One hypothesis suggests that Pangea's tectonics and geography reduced coastal marine habitats. The joining of continents decreased the area of continental shelves, those shallow water regions teeming with marine life. This habitat loss could have made marine species more vulnerable to extinction by concentrating them in a smaller area, thus increasing their expo to environmental changes. However, the evidence for this effect remains uncertain. It's difficult to definitively say that the reduction of continental shelf area directly caused extinctions, even if it likely weakened marine ecosystems before the Permian crisis. Another intriguing idea links the shrinking seafloor to the Permian-Triassic extinction. The formation of Pangea slowed the spread of mid-oceanic ridges where the ocean floor is formed. Volcanic activity cooled and sank the oceanic crust, leading to a drop in sea level and reducing the number of islands and isolated marine environments. I often wonder about the last strongholds, the final refuges against extinction. Imagine a world undergoing immense environmental crisis, and only a few places remain untouched, offering sanctuary to life. Then imagine even those vanish. The formation of Pangea, while unifying the world, also brought species from different continents together, species that were once separated. While this mixing could have created new ecological connections, it also led to a loss of biological diversity, as endemic species were displaced from their unique niches. It's a strange paradox. Unity creating loss. Even within Pangea, climatic barriers persisted, separating ecological communities. Despite its unified geography, the supercontinent experienced intense climatic changes, with extreme weather hindering the spread of some species. Think of intense monsoons or vast temperature variations between the equator and the poles. During the Pangea era, there may have been continental refugia, havens that ultimately disappeared during major volcanic events. One such place might have been the region that didn't fully join Pangea in southern China. But the eruption of the Ameishan traps before the Permian Triassic extinction likely destroyed this last stronghold. Later, as the Mesozoic era drew to a close, Pangea began to break apart, leading to the separation of huge landmasses and the formation of the continents we know today. This division significantly changed the evolution of ecosystems as species became isolated from each other and developed separately. This fragmentation contributed to the diversity of terrestrial life. During the Carboniferous period, the vegetation was lush and dense, creating a rich habitat for a variety of fauna. This vast territory occupied most of the globe, encompassing humid tropical zones and arid deserts. The Carboniferous forests included giant lycopods, some of the earliest vascular plants on the planet, with stems covered in scales that could grow to 40 meters in height. These forests formed vast swamps. But by the end of the Permian period, these trees gradually disappeared, perhaps due to climate change. It's worth noting, though, that these trees contributed to soil formation. Coal deposits discovered from this period were formed by horsetails, plants capable of growing into trees within just 5 to 10 years. Ferns were also an important part of Pangea's flora, including tree ferns like Cerone, which reached heights of up to 10 meters. By the end of the Carboniferous period, seed ferns, known as permaphytes, appeared, marking a transition from spores to seeds. This allowed plants to adapt to new conditions and move beyond humid habitats, taking advantage of the arid lands of Pangea. The genus Glossopteris, for example, was widespread in the southern regions of Pangea, creating vast forests. The tongue-shaped leaves of these plants could reach lengths of 2 to 30 centimeters, contributing significantly to the evolution of terrestrial ecosystems. Their fossil remains play an important role in understanding ancient flora and plate tectonics, indicating a warmer climate in the past and a distribution associated with the supercontinent of Gondwan. As the climate changed at the end of the Carboniferous and into the Permian period, with alternating periods of glaciation and warming, new plant species emerged, including cycads and chides, palm-like gymnosperms that flourished in tropical and subtropical regions. I find it remarkable that certain species can survive mass extinctions. The gymnosperm forest, for instance, those trees that dominated during the time of Pangea, possessed an almost unbelievable resilience. They just kept adapting. It makes you wonder what secrets they held, what mechanisms allowed them to flourish even as the world around them changed drastically. During the Pangea era, coniferous trees began to appear, dotting the landscape with their cones and needles. These plants, showing real evolutionary progress, were particularly suited to drier climates. However, despite this, these forests often experience periods of rapid growth, followed by times of stagnation due to seasonal climate shifts or unpredictable weather. It was in this harsh environment that gymnosperms evolved, allowing them to survive and diversify. Some of those very species are still with us today. During the Mesozoic era, plant life changed significantly, spreading to the planet's equatorial regions. The humid climate encouraged the growth of diverse deciduous forests, including species like Araucaria and Podocarpus, which flourished in temperate and subtropical climates. In areas with consistently high humidity, coal bogs or peat bogs began to form. These areas, typically located near the equator, were rich in vegetation and organic matter that, during decomposition, formed carbon. But the formation of Pangea, a process spanning millions of years, profoundly altered the climatic and environmental conditions that had fostered these swamps. The result was a sharp decline in coal deposits, a pivotal consequence of the supercontinent's creation. This reduction stemmed from a change in the intertropical convergence zone, those regions of low temperature and high press near the equator where trade winds converge, causing regular precipitation due to their large surface area. Pangea's formation brought significant changes to this zone, impacting the distribution of rainfall across the supercontinent. Precipitation decreased in inland areas, even those previously close to the equator, creating drier conditions and reducing the moisture content of coal swamps. The assembly of Pangea led to an extreme monsoon climate, marked by an increase in the number of dry and wet seasons, which created unfavorable conditions for swamp formation. These climatic shifts contributed to a decline in coal reserves, reaching historically low levels during the Permian period around 300 million years ago. At that time, significant coal deposits were scarce, except for microcontinents in northern and southern China. These regions, not yet fully integrated into Pangea, maintained more stable and humid conditions, conducive to swamp formation and, consequently, coal deposits. During Pangea's existence, both terrestrial and marine fauna underwent significant diversification, a direct result of the supercontinent's formation at the end of the Paleozoic era. From its emergence at the beginning of the Mesozoic era, this geographic configuration fostered unique conditions that promoted the emergence and adaptation of many species. Pangea's tropical oceans teemed with life, from primitive fish to giant marine reptiles. The Tethys Ocean, located to the east of Pangea, hosted incredible marine biodiversity. Coral reefs flourished there, alongside large marine predators like ichthyosaurs and plesiosaurs, creating a rich and dynamic ecosystem. The marine fauna of that period were constantly adapting to significant fluctuations in sea level caused by climate change. These waters were home to numerous ammonites, mollusks with spiral shells, as well as brachiopods which filtered water for food, attaching themselves to rocks. Ichthyosaurs, marine reptiles resembling dolphins, hunted underwater. In the tropical seas of Pangea, they became the first reptiles to fully adapt to aquatic life. These creatures lived not only in coastal waters but also far offshore, Fossils of ichthyosaurs discovered even at high altitudes suggest their marine habitat was very different from modern conditions. These aquatic environments teemed with diverse fish species, showcasing the incredible adaptability of marine organisms. Ray-finned fish and lobe-finned fish dominated these changing ecosystems. These fish became the prototype of tetrapods, highly adaptable forms that evolved in the rivers and lakes of the supercontinent. They thrived in the shallow seas surrounding Pangea and played a crucial role in the ecosystems of the time. By the end of the Triassic period, reptiles, initially small in size, gradually evolved, leading to the emergence of large and impressive dinosaurs. The Mesozoic era stands as a testament to the rich diversity and amazing adaptability of the species that inhabited Pangea. Among them, the therapsids, ancestors of mammals, stood out. These included carnivores like gorgonops and herbivores like dicynodonts, which successfully adapted to Pangea's arid conditions. It's believed that Sarcosaurus lived in the late Permian period and gave rise to the lineages that led to the emergence of dinosaurs, including species like Herrerasaurus and Eoraptor. Imagine a world dominated by reptiles and amphibians, a world where the ancestors of mammals were just beginning to adapt. I've spent years studying this era, and it still fills me with a sense of wonder. Picture Pangea, the supercontinent, teeming with life both familiar and alien. It was a time of transition, a prelude to the age of dinosaurs and, eventually, us. Within this diverse environment, insects like the Meganeura thrived. Giant dragonflies hunted in swamps, while beetles and orthopterans adapted to Pangea's vegetation. Though birds were yet to appear, flying reptiles like Therosaurus already soared through the skies, foreshadowing the evolution of flight. Dinosaurs like Chelophysis roamed the vast deserts and plains, their presence shaping the landscape. These semi-arid plains served as a training ground for the dinosaurs' future dominance, a reign that would solidify after Pangea's breakup. Amidst scattered forests of cycads and conifers, iconic species thrived, ruling terrestrial ecosystems for millions of years. During this time, the first true mammals emerged, small and unassuming compared to the mighty dinosaurs. Yet, they carried within them the potential for more advanced groups, poised to evolve rapidly after the dinosaurs' eventual extinction. The fauna of Pangea paints a picture of exceptional biodiversity, a testament to life's constant adaptation to changing environmental conditions. It's important to remember that Pangea also witnessed the largest mass extinction in Earth's history, occurring at the end of the Permian period. This catastrophic event triggered radical shifts in the planet's ecosystems, and the recovery was incredibly slow, spanning millions of years. Nevertheless, it was during this period that the first dinosaurs and primitive mammals began to appear, marking a crucial step in the evolution of life on our planet. The breakup of Pangea unfolded in three distinct stages, each contributing to the formation of the oceans and the gradual separation of the continents. The initial phase, commencing in the lower Middle Jurassic period, signaled the beginning of the rupture. A significant fault line emerged between the Tethys Ocean to the east and the Pacific Ocean to the west. This geological rift primarily occurred between the North American and African tectonic plates, resulting in the formation of several faults, including the Mississippi River Fault, which eventually led to the birth of the Atlantic Ocean. However, the emergence of the Atlantic Ocean was not uniform. The central part of the North Atlantic remained closed until the Cretaceous period. During this time, the supercontinent of Eurasia, uniting North America and Eurasia, began to rotate clockwise. This movement caused North America to shift northwards and Eurasia southwards, leading to the gradual close of the Tethys Ocean. This had a profound impact on the future geography of the Mediterranean region and the Middle East. On the opposite side of the African continent, along its borders, other tectonic shifts were underway. Near East Africa, Antarctica, and Madagascar, new tectonic faults began to form, foreshadowing the future emergence of the Southwest Ocean. The Indian Ocean, during the Cretaceous period between 150 and 160 million years ago, experienced significant faulting, gradually separating Africa from Antarctica and Madagascar. The second major phase of Pangea's fragmentation began in the early Cretaceous period, between 150 and 140 million years ago. This event marked a pivotal stage in Earth's geological evolution. At that time, the supercontinent of Gondwana, encompassing Africa, America, India, Antarctica, and Australia, began to divide into several continental blocks, a division that would decisively shape the modern continents. This process began when the small continent of Cimmeria collided with Eurasia approximately 200 million years ago. Years later, this collision led to the formation of a subduction zone, the Tethys Trench, which likely played a crucial role in the contraction of the Tethys Ocean, a vast internal sea. This process may have driven the northward movement of continental masses such as Africa, as well as the movements of India and Australia. Tectonic forces highlighted the division between Western Gondwana, comprising Africa and South America, and Eastern Gondwana, including Antarctica, India, and Australia. This separation resulted in the formation of a new ocean, the Indian Ocean. South of this process, the ocean in the South Atlantic began to form. The opening of the South Atlantic was accompanied by a special dynamic of movement from south to north. Like geological lightning, South America began to drift away from Africa, gradually carving out a new ocean. This ocean became an important corridor for oceanic communication between the southern and northern hemispheres. I sometimes imagine the immense forces that shaped our world, forces that continue to work even now. The story of Pangea is one of such forces. Its breakup, starting in the mid-Jurassic period, wasn't just a geological event. It was a biological catalyst. It shattered a supercontinent into the pieces we now know as our continents, forever changing the course of life on Earth. Around the same time, in the north, Madagascar and India began their own secession from Gondwana. Antarctica, opening the way to the Indian Ocean, and Madagascar, continuing their northward movement, became key elements in these tectonic processes. India, after briefly joining the African plate, slowed its movement but then continued its rapid northward journey at an incredible rate of 15 centimeters per year. This relentless advance gradually closed the Tethys Ocean. Over millions of years, India's collision with Eurasia would lead to the formation of the Himalayas, mountains born from the immense press of two tectonic plates colliding. Tectonic activity in India between 190 million years ago finalized the separation of Australia and Madagascar from the mainland. While Madagascar continued its northward trek, joining the African plate, Australia stabilized on the east coast of Africa and began its own separation from Antarctica, migrating northeast. These tectonic shifts led to the formation of the Coral and Tasman Seas and also separated New Zealand and New Caledonia, sending them eastward to become isolated islands in the vast Pacific Ocean. The final breakup phase of Pangea occurred in the early Cenozoic, a period from the Paleocene to the Oligocene, witnessing profound changes in the planet's geological structure. During this era, North America and Greenland began to drift away from Eurasia, giving birth to the North Seas approximately 60 to 55 million years ago. This separation was accompanied by the continued expansion of the Atlantic and Indian Oceans, further contributing to the close of the Tethys Ocean. Simultaneously, Australia also experienced separation from Antarctica. Antarctica began a rapid northward movement, similar to India's earlier journey, more than 40 million years before modern Australia emerged. Even from the beginning, Antarctica was near or at the South Pole. This had a significant impact on the climate and glaciation of the region over millennia. Roughly 60 million years ago, India collided with Asia, leading to the formation of the Himalayas and the Kielow of the ancient Tethys Sea. This collision continues even now, with India still moving north, increasing the press on tectonic plates in the region. At the same time, the African plate began to shift direction, moving from west to northwest towards Europe. South America also began its northward journey, moving away from Antarctica. This movement allowed for the creation of a complete ocean circulation around Antarctica for the first time, which caused rapid melting and formation of glaciers. During this period, the Earth's global climate underwent significant changes, including the formation of the Gulf of California, the rise of the Alps, and the creation of the Sea of Japan. These events reshaped the planet's topography and impacted biodiversity in both marine and terrestrial ecosystems. Even now, the process of Pangea's breakup continues in the East African Rift, where tectonic plates continue to diverge. These ongoing collisions suggest that a new supercontinent could form within a few 100 million years. The formation of Pangea played a key role in the mass extinction at the end of the Permian period, particularly devastating for marine life. As the supercontinent merged, shallow water ecosystems shrank, leading to dire consequences. The creation of vast land barriers hindered the circulation of cold polar waters towards warmer zones, decreasing dissolved oxygen levels in tropical regions, exacerbating the ecological crisis and contributing to the loss of approximately 95% of species diversity. However, the collapse of Pangea also spurred changes that led to the formation of new shallow water habitats. As the total coastline increased, many bays formed, opening up new environments for marine life. The opening of channels between small land masses also contributed to the flourishing of life, allowing warm and cold ocean waters to mix increasing marine diversity and leading to the emergence of new species. On land, the fragmentation of Pangea significantly impacted plant and animal populations. The division of these groups into new isolated continents fostered unique adaptations to new conditions. These adaptations, evolving in response to selection praise in different habitats, contributed to the increased biodiversity of the species that survived this period. Evolution took place in response to diverse environmental conditions, leading to biological diversification across the globe. The breakup of Pangea. I find myself thinking about it often. What an unprecedented event for so many ecosystems, with such profound consequences for life in the seas and on land. The fragmentation of continents led to the isolation of countless species. As land masses separated, new barriers arose: oceans, mountains, deserts. This, in turn, spurred the emergence of entirely new species through speciation. Populations of animals and plants, isolated in their own corners of the world, evolved in unique ways, driving biological diversification. Think of the Australian mammals, the marsupials, evolving independently from their counterparts on other continents. Or the changes in climate, the inevitable consequence of Pangea's fragmentation. What was once a vast, unified continent gave way to a mosaic of regional climates, each fostering the development of distinct ecosystems: tropical forests, grasslands, tundra zones. The creation of new coastlines softened the blow, increasing the number of marine habitats and encouraging the growth of coral reefs, mangroves, and other coastal ecosystems, thus boosting coastal species diversity. But this dynamic wasn't favorable for all. Some species colonized new territories, while others teetered on the brink of extinction, unable to adapt. These new conditions also led to collisions between species of different origins, much like what happened when North and South America joined via the Panama Land Bridge. The breakup of Pangea also shaped the development of modern ecosystems. Geological processes, like shifts in ocean currents, created entirely new habitats, fostering unique biological interactions. These currents redistributed nutrients and influenced water temperatures, leading to the emergence of new marine species adapted to these specific conditions. The separation of continents significantly impacted food chains. Organisms had to adapt to new food sources and habitats. Vegetation diversity and geographic fragmentation led to herbivores and their predators evolving together in specific ecological niches. The formation of these individual ecosystems as a result of these geological processes had a long-term impact on the flora and fauna of modern biogeographical regions. Modern regions like the Neotropics, Ethiopia, and Australasia are all children of these ancient transformations. The breakup of continents also contributed to the emergence of endemic species, like the lemurs of Madagascar and the kangaroos of Australia, evolving in isolation. These creatures witnessed the breakup of Pangea, one of the largest geological events in Earth's history. The consequences of this event are still visible in the distribution of species across the planet. Pangea disappeared millions of years ago, yet its legacy remains firmly rooted in the landscapes, species, and climate of our world. It reminds us that our planet is in a state of constant transformation, an endless journey through changing weather. If the Triassic and Jurassic periods were eras of violent movement and radiation, the Cretaceous was no exception. It, too, was characterized by significant biological changes and events that affected both the plant and animal world. Flora and fauna from the Cretaceous period have long since vanished, but their deposits eagerly await, ready to tell us their story. So let's begin exploring it. The Cretaceous period was the longest of all the Mesozoic periods, spanning roughly 80 million years, from approximately 145.5 million years ago to 65.5 million years ago. This long period is divided into 12 subsystems, each with its own unique characteristics. Over the years, the face of the Earth has changed in accordance with the rhythm of geological activity. The preceding Jurassic period was quite warm and humid, with only minor changes. After a period of cooling at the start of the Cretaceous, the climate once again became warm and humid towards the end. Average temperatures exceeded 18 degrees and approached 20 degrees. To put that in perspective, the average temperature on Earth in 2023 was about 15 degrees. There were no polar ice caps, indicating that the climate remained relatively warm, as it had throughout most of the Jurassic period. Not long before, there was only one continent in the world, Pangea. But during previous eras, under the influence of climatic and geological changes, this continent gradually broke apart into fragmented land masses. Two continents formed, Laurasia in the north and Gondwana in the south. By the end of the Jurassic period, the world was changing. The continental waltz, it was far from over. As I pore over maps of the Cretaceous period, I'm struck by how much our planet was changing. While the northern regions saw slow shifts, the south was birthing entirely new continents. If we could look back, we'd notice some familiar shapes emerging, almost like a rough draft of the world we know today. It was during this era that our blue planet began to resemble its modern form. We call it the blue planet because water dominates its surface. But there's a crucial detail we often miss. During the Upper Cretaceous, the sea level was dramatically higher, some 200 to 300 meters above what it is now. Imagine how that reshaped the landscape. Entire continental landmasses were submerged by waves, a phenomenon we're seeing echoed in parts of Europe today. Instead of large connected landmasses, the world was more of an archipelago. And these rising sea levels weren't just redrawing coastlines, they were influencing the climate itself. We've seen the lush vegetation of the Triassic and Jurassic periods supporting a diverse range of species. Most of the plants of that time were conifers, varied in their own right, but the Cretaceous period saw a true evolutionary explosion. This was the era when seed-covered plants first appeared, angiosperms, or flowering plants. Imagine the impact this had on a world previously dominated by deciduous and coniferous trees, many of which relied on cones. The arrival of angiosperms transformed the plant kingdom, opening up new avenues for evolution. Flowers bloomed, new species emerged, and insects found new ecological niches to exploit. By the end of the Cretaceous period, these seed-covered plants had become the dominant group. One of the earliest examples is Archaeophractus, an aquatic plant found in lakes and ponds. We know of 3 genera, Fructus arcavus, Fructus ephora, and Fructus arcleanengensis, as well as Fructus arcsinensis. These plants, usually less than 50 centimeters tall, had lacy leaves and roots typical of aquatic life, reproducing through seeds. What's fascinating is that they can be divided into groups with distinct male and female plants, while others show minimal sexual differences, exhibiting bisexuality. Another key discovery was the Montesquidal species, an aquatic plant found in the Spanish peninsula, specifically in the Pyrenean mountain range. Fossils of this plant have been unearthed throughout the Cretaceous period in the Cunco province. Its classification has been debated by paleobiologists for decades, but it is now largely accepted that Montesquidale could be one of the earliest flowering plants on Earth. We owe this discovery to Bernard Gomez and Véronique Devereaux, two European scientists whose work has shed new light on these ancient plants. Their analytical methods allowed them to study fossils from new and unexpected angles. Gomez, for instance, uses carefully measured doses of hydrochloric acid. A single drop can reveal millimeters of a plant, leading to the identification of previously undetectable features. This is how the equia was discovered, a term denoting a previously unseen part of the plant. Why is this anatomical feature so significant? It reveals the stomata, the tiny pores through which plants absorb carbon dioxide. The structure and function of these stomata differ greatly between terrestrial and aquatic species. In the case of Montezoa equia, the stomatal apparatus perfectly aligns with the lifestyle of an aquatic plant. It also confirms that it is a covered seed plant producing fruits with a protective shell known as a carpel, which shelters a single seed. These plants also have smaller leaves and a large number of stomata and veins, allowing for high rates of transpiration and photosynthesis. The fruits and wrappers provide crucial protection for seeds and pollen in the aquatic environment. As the climate warmed and sea levels rose during the mid-Cretaceous, seed plants began to colonize lowland forests, competing with ferns and conifers. This competition may have been a key driver of their evolution, and this undoubtedly benefited the entire ecosystem. The first to capitalize on this new ecological niche were pollinators. The interaction between pollinators and flowering plants. It's a dance I find endlessly fascinating. It's called coevolution, this process by which two species intricately influence each other. There's a competitive aspect like predator and prey or parasite and host. But then there's the cooperative side when species depend so completely on each other, a mutualistic relationship. When I consider the prez to find a niche in an already thriving environment, I think about the major changes life cycles undergo. Plants and insects, though, they're a powerful, adaptable team. Flowering plants need pollinators, and they've evolved to attract them, all while remaining safe. They show off with beautiful petals, bright shapes, sometimes more extravagant than usual. They emit sweet aromas, produce irresistible nectar. Butterflies, wasps, they can't resist. As insects adapt to new habitats, they acquire new characteristics. Nectar tubes gradually replace the mandibles of some butterflies, for example. Seed plants, unlike gymnosperms, sometimes have poisons in their ovules as a defense, but insects that can digest them gain access to resources without competition. It was during this period that the bee appeared, or at least its most distant ancestor, Melidosphex burmensis. It's a tiny insect, only 3 millimeters long. We often marvel at how some insects grow to such enormous sizes, but with Melidosphex, it's the opposite. Its small size compared to modern bees is amazing. This Melidosphex belongs to the family Aphoidea, dating back to the Jurassic period. Judging by its silhouette and anatomy, it's somewhere between a wasp and a bee. Very similar to wasps, but with branched hairs reminiscent of bee hairs. This Melidosphex was found stuck in plant resin, living out its last hours, preserved in amber, fossilized resin found in modern-day Burma in the Hukong Valley. It allows us to witness the Cretaceous period, and it's not alone. Many other insects suffered the same fate. 2 species of ants were found in amber, the house ant, also known as the cockatoo ant, and the unicorn ant. Both existed millions of years ago. Researchers discovering them in the same fossil burial ground believe they're close relatives. But let's return to our possible bee ancestor, Melidosphex, and other pollinating insects. Initially, these insects were carnivorous and probably solitary. They specialized in a certain type of flower, but to adapt and survive, they had to unite. Unity is strength, and eusociality became their best way of existence. Depending on their role in the colony, these insects don't specialize in a particular type of flower. Some care for the larvae, others build nests, defend it, or search for food. This phenomenon appeared several million years ago, in the middle of the Million period. During that time, creatures capable of amazing feats emerged, belonging to the tribe Corbicula, numbering thousands of different species. While eusociality has been a major achievement for some insects, allowing them to survive and adapt, others found very different ways, like dragonflies and stick insects. One of these methods was melanogenesis, a process by which organisms can change their color. Some species used melanogenesis for camouflage, becoming virtually invisible. Inexperienced creatures may have thought they could survive by being active at night, when predators are usually less active. They believed they could avoid attacks, especially when the reptile dance ended and the flying and sleeping animals sank into a peaceful silence. But the forest, even with the moon in place of the sun, concealed danger. Now, surrounded by darkness, silence, and stars, everything seems lifeless. Calm herbivores, carnivores, and insectivores fall into a deep sleep. But we shouldn't overlook the subtle movements in the thickets. Weeds, small mammals that live in this vegetation, must be wary. They are so invisible that you'd have to hurry to see them, even for a moment. Only at night do they dare leave their nest to enjoy a dish made with insects. It's easy to forget about these creatures when we think of the Mesozoic era still associated with dinosaurs. While it's true that dinosaurs were the main inhabitants of our planet at that time, they were far from the only ones. The dominant mammals of the Cretaceous period were dinosaurs, but they were able to find their place and their way of life. At first glance, their physical possibilities seem modest compared to the dinosaurs, but this would become their main weapon in the fight against a large-scale crisis that would break out in several million years. But more on that later. For now, let's get back to our insects and our new species. Plant insects took full advantage of the appearance of the covered seed plants. However, these aren't It's strange to think that there was a time when no animal on Earth ate only plants. I find myself picturing those ancient landscapes, trying to grasp how different the world must have been. Before the Cretaceous period, that was the reality. But then, herbaceous plants emerged, and everything shifted. These new plants weren't just food, they were camouflage for snakes, a place for them to hunt smaller prey in the humid forests. I imagine these early snakes, some still with legs, moving through this new grassy world. Our rhinogrin, for example, still had hind legs, ankles, even a few toes. It hunted at night, going after smaller prey. It's hard to believe that from these creatures the titanoboa would eventually evolve, becoming one of the most formidable predators. But even before the titanoboa rose to prominence, the Cretaceous period was teeming with large predators on land, in the sea, and in the air. The dinosaurs, like the plants, were evolving rapidly. Climate changes forced them to adapt, migrate, and develop in remarkable ways. Take the giants, for instance. Dinosaurs had been around since the Triassic, but they really took over in the Jurassic. And by the Cretaceous, their evolutionary radiation had exploded. I remember reading about Argentinosaurus, found in South America, and Paralititan, discovered in Egypt. Both were among the largest and heaviest creatures to ever walk the earth. Argentinosaurus could reach 8 meters in height, 35 meters in length, and weigh almost 80 tons. Its tibia alone was over 1.55 meters long. Paralititan, no less impressive, held its own against its American contemporaries. Of course, estimates of these prehistoric animals are constantly being revised as we find new fossils and develop new technologies. Kenneth Carpenter, a paleontologist, did a comparative study of Saltosaurus and estimated that the Egyptian specimen was between 30 and 40 meters long. In other parts of the world, creatures reaching 10 meters in height and weighing nearly 60 tons have been discovered. In 2021, the remains of Australotitan cooperosus were identified, a dinosaur believed to have been just over 6 meters tall and about 100 meters long, and about 25-30 years old at death. What happened to the Diplodocus and Brachiosaurus from the Jurassic? Other giants would fill their ecological niche. The sheer size of these creatures meant they needed a lot of energy. They weren't picky eaters, consuming cycads, conifers, palms, grasses, and even the ancestors of rice and bamboo. And they seemed to live in groups, the females digging nests to lay around 20 eggs, covering them with vegetation and earth. I can picture the size of those nests, a deterrent to some predators, but not to all. Living in groups increased their chances of survival, as did their skin, covered in a kind of armor of small scales. Beyond these giants, the Cretaceous period also saw the rise of the Ceratops, a group of animals that first appeared during the Jurassic period, initially as bipedal creatures, the Triceratops. Even the name itself sounds like something from a dream, doesn't it? 7 to 10 meters long, almost 4 meters high, and weighing up to 8 tons. An impressive herbivore roaming the earth. I remember the first time I saw a Triceratops skull in a museum. It made up almost a third of the total body length, a well-protected fortress in itself. During the Millennium period, the ancestors of Triceratops began adapting to their environment, slowly shifting from walking on 2 legs to all 4s. This period also saw the emergence of a new genus of ceratopsians, becoming 4-legged and more heavily built. This evolutionary path eventually led to the incredible diversity we see in the fossil record, especially during the Cretaceous. Among these, the Neoceratopsians certainly stand out. And of course, the Triceratops, a favorite of children and adults alike. That massive head was equipped with a huge horn protruding from its muzzle and two more towering above its eyes. These features weren't just for show. They were meant to intimidate any predator that dared to attack. Unlike some other ceratopsians, the Triceratops had a particularly strong shield, leading many to believe it was crucial for combat. However, more recent research suggests the frill and horns may have served other purposes. Some scientists now hypothesize these unique features acted as a form of identification, perhaps even used to determine dominance among males within the herd. This theory is supported by the discovery of holes in some frills, possibly caused by clashes during disputes. Interestingly, the skull of Torosaurus, once considered a separate species, is now believed to be the adult form of Triceratops. This massive creature needed solid support to move, hence the strong limbs and heavy body. Its powerful legs ended in three-fingered hands, allowing it to walk on its toes using both front and back legs. Some even suggest the toes may have evolved into hoof-like appendages. There's also speculation that Triceratops was a social animal, living in herds or even alongside other large herbivores. However, research on this aspect is limited, and the available fossil evidence doesn't definitively confirm or deny this hypothesis. Now, while some dinosaurs undoubtedly had feathers during the Jurassic period, it became a much more common trait during the Cretaceous. Take, for instance, the Microraptor. Compared to the massive Triceratops, it was tiny, only about 80 cm long and weighing just over a kilogram. Fossil remains have revealed feathers all over its body, including its legs and a long tail. In 2012, American and Chinese researchers made a fascinating discovery about Microraptor's feathers. They found they were black, elongated, and arranged in sheets. But more than that, the arrangement indicated iridescence, the ability to change color depending on the viewing angle or lighting. And not long before that, in 2011, fragments of feathers preserved in amber were found in Canada, along with fragments of hair. Hair and feathers served different functions for these dinosaurs. In some, these adaptations helped them withstand the long, harsh winters that were common in certain regions. These discoveries are opening up new possibilities in the study of ancient creatures. Feathers helped conserve and maintain body heat, crucial for coping with the cold. Some species also used them for flight, though gliding was likely more common among feathered dinosaurs than full-fledged flight. Over time, evolution led to new uses for feathers. Consider the Salus, a creature that didn't fly but still found a unique purpose for its plumage. This particular male had a pegastyle, a bone in the sacrum formed by fused tail vertebrae. This small detail played a key role in its appearance, allowing it to move its feathers and attract the attention of females. And now we find ourselves in the heart of a lush equatorial forest. The plants here thrive on the heat and high humidity. Grapevines, small bushes, ferns, and flowering plants flourish in this jungle paradise, benefiting from the abundant sunlight, moderate temperatures, and ample water. However, just a few meters away from this idyllic scene, you might encounter an ankylosaurus, another dinosaur well loved, especially by children. Known for its bony, club-like tail, the ankylosaurus was a formidable creature. Imagine an animal reaching almost 10 meters in length and weighing about a ton. Its tail club, proportionate to its body, could weigh at least 50 kilograms. The question then arises, is it true that the ankylosaurus used its tail club for defense? While we should approach such statements with caution, there's good reason to believe it did indeed use it as a defensive weapon. Concentrating its power on the tip of its tail, it could deliver incredibly powerful blows, capable of breaking bones. Few enemies would dare to risk such an attack, but if you look closely, you'll see that the ankylosaurus's tail wasn't its only advantage. It also possessed excellent armor, designed not for attack, but for protection. Like the tail, the armor covering its body consisted of bony plates known as osteoderms. It also had thick scales and large horns on the top of its head. The skull, with its entire defensive array, must have looked quite impressive. An impenetrable fortress. A dinosaur's only real weak spot? Its stomach. Scientists believe this area is particularly vulnerable, and I find that fascinating when I consider their behavior. To protect itself, a dinosaur would throw its club at an attacker the moment it had the chance, trying to land a powerful first strike. This adaptation, this instinct, helped them survive in harsh conditions, surrounded by predators seemingly fiercer than the last. Nature, in its way, allowed them to evolve, to adapt not just to their habitat, but to the dangers within it. The Tyrannosaurus rex, king of the dinosaurs and perhaps the most famous of them all, lived in what is now the United States. We've known about it since the 1900s, but even now, it continues to amaze us, revealing new facets of its mysterious nature. Why would a giant, reaching 13 meters in length, almost 4 meters in height, and weighing a staggering 10 tons, have such comically small arms? It seems illogical, doesn't it? But nature is rarely illogical. Researchers initially thought the T-Rex's hands were simply in the process of becoming less functional through evolution. But further investigation revealed bony ridges on the arm bones, suggesting muscle reinforcement. This gives us a completely new perspective. Perhaps the Tyrannosaurus used its small hands to maintain balance, maybe even to help it jump into water. Chasing prey might not have been its forte, but it could reach speeds of up to 20 kilometers per hour. And here's something else. Paleontologists discovered in 2014, based on research in Canada, that contrary to popular belief, the T-Rex wasn't a solitary creature. They moved in groups. Tracks show that these massive animals moved in parallel, a topic still under study. Finally, the Tyrannosaurus was warm-blooded. In warm weather, its body temperature would have been between 35 and 30 degrees Celsius. Unfortunately for its prey, its metabolism was incredibly fast, requiring a lot of meat to sustain its energy needs. The T-Rex wasn't a picky eater, attacking all kinds of dinosaurs. Its diet mainly consisted of ceratopsians, including Triceratops. Now, let's journey to another continent. Africa, now known as the home of lions, was once home to the Spinosaurus. During the Cretaceous period, the Spinosaurus was one of the largest predators on the continent. though less is known about its life and behavior. It was a formidable hunter, adapted to both its habitat and the available prey. Spinosaurus might have primarily eaten fish, but it could also easily attack young dinosaurs or even bison thanks to its sharp teeth. They were active and didn't hesitate when faced with potential prey. How did the Spinosaurus hunt, and what position did it adopt during an attack? These questions remained unclear until 2014. The discovery of its rear limbs was a breakthrough, allowing scientists to piece together new hypotheses. These hypotheses suggest the animal was quadrupedal, with relatively short front limbs, shifting its center of gravity forward. Some researchers believe it may have been semi-aquatic, like a crocodile, but this remains a hypothesis requiring further research. Let's now turn to a European predator, a member of the genus Arquator, belonging to the family Abelisuridae. This animal was undoubtedly bipedal, with a large skull and short, sharp teeth. Its diet, however, raises more questions. It was certainly carnivorous, but it might also have been a scavenger. This theory is supported by its forearms and forefingers, which could have been used to extract entrails. Yet it also possessed a powerful neck, supporting the theory of its predatory nature. With such a neck, it could repeatedly bite and weaken its prey until it succumbed. The tropical climate during the Cretaceous period fostered lush vegetation and a unique ecological niche, facilitating the proliferation of various dinosaur species, including titanosaurs like Elasmosaurus, small predators like radin, knot-toothed orids, and herbivores like the fern-eating Astasaurus. While carnivorous dinosaurs found ample food and reproductive opportunities, not all could adapt to the changing conditions. Some struggled, while others failed completely. Some species, despite successful evolution, couldn't adapt and went extinct, gradually disappearing, as seen with the stegosaurs and Allosaurus, two large predators from the Jurassic period. It's a strange thought, isn't it, that the very animals that shared the earth with dinosaurs, creatures that seemed destined to be footnotes in their story, are actually our ancestors. For a long time, I think we assumed that mammals were just a minor presence, waiting for the dinosaurs to disappear before they could truly flourish. But the reality, as is so often the case with deep history, is far more nuanced. The end of the Cretaceous period wasn't a clean slate. It wasn't as if the dinosaurs vanished and suddenly mammals inherited a completely empty world. Instead, there was a reshaping, a struggle for survival where some species adapted and others simply couldn't. The dinosaurs, despite their dominance, were among those who couldn't fully adapt. But what about the mammals? They shared the same dangerous world as the dinosaurs, filled with formidable predators. It's easy to imagine them as insignificant, but they managed to survive, even if they didn't exactly thrive. And we as humans are part of that very group. It turns out mammals had a secret weapon, or rather, two: their small size and their lifestyle. They carved out a niche, a way to survive alongside giants without becoming prey. You could say they lived by the principle: to live happily, live secretly. Fossils from the Mesozoic era tell the tale. Even when the first dinosaurs walked the earth, mammals were already there. We find their remains from the Triassic period, like Basileus adeli, and from the Jurassic, like Kishu. Their smaller size made them far more stealthy than the dinosaurs. By the Million period, mammals had diversified, becoming more numerous in a variety of forms. We see evidence of almost every type of diet, from vegetarians to insectivores. While many might seem less fearsome than the dinosaurs, that doesn't mean they were harmless. Take Rapanomamus, for instance. It was a massive creature similar to the Apoma, and its courage certainly wasn't proportional to its size. Remarkably, remains of the herbivorous dinosaur Gtakasaurus have been found in its stomach, dating back 130 million years. This shows that even these early mammals were capable of attacking dinosaurs when necessary for their survival. Most of these early mammals had fur and could produce their own heat, a rare trait in the animal kingdom. They didn't need to rely on the environment for warmth, unlike the dinosaurs. They were tiny, most no more than 10 centimeters long, resembling small mice or shrews. But this apparent weakness was actually their strength, allowing them to navigate the dinosaur world with greater ease. The plains were ruled by dinosaurs, the oceans by reptilian sailors. Moving through such a hostile environment was a challenge, unless you were small and fast. Mammals were almost invisible, able to avoid the attention of the giant predators. And there was another key difference. Most mammals were nocturnal. While the large predators were active during the day, the small mammals could safely forage in the dark. They found shelter in small burrows, dense vegetation, and underground tunnels, remaining hidden from predators for hours. If they were caught out at night, they could escape with relative safety. It reminds me of the saying, "When the cat's away, the mice will play." These early land mammals, with their rat-like builds, would venture out in search of food while the great predators slept, waiting for sunset to emerge under the cover of darkness. To hunt successfully at night, these Cretaceous mammals developed new skills. Of course, not all creatures could thrive in the dark. Many animals of that period had poor hearing, which made it difficult for them to. I find it remarkable that even as dinosaurs roamed the earth, mammals were quietly solving the problem of hearing in the dark. While other animals relied mostly on sight, mammals began to depend on their ears. The development of those tiny bones in the ear was a complex process, so small that they often go unnoticed in fossil skeletons. But their significance is undeniable. During the Million period, a real evolutionary breakthrough occurred, and various species of mammals began to actively develop. Take the aramids, for example, which appeared in the Triassic and still exist today. They became an integral part of the Cretaceous period's fauna. These Cretaceous animals were protein-like creatures with long tails, almost like cats. Their ability to hear and live at night wasn't fully developed yet, but they survived thanks to their arboreal lifestyle. They ate not just fruit and seeds, but insects too. And in case of danger, they could use skin membranes called Pangeos to glide between the trees. Among the Cretaceous animals, there was also a herd of disease, resembling a shrew. It reached a length of about 20 meters, had an elongated muzzle and very large eyes. The teeth of the haul-on pain allowed it to feed on a variety of things. Insects, like most of their relatives, are small animals, so they don't require a lot of food to survive, which helped them survive the age of dinosaurs and would help them overcome the coming crisis. But let's turn our attention to another representative of a large group of mammals called Dentiocutus. This representative belongs to the Drolus odia clade, which inhabited the Upper Cretaceous, taking advantage of the adaptations I've described. Cropintiocutus was small, about the size of a mouse, with a thin muzzle, well-developed and long, round eyes, and sharp fangs, which allowed it to feed on insects and small invertebrates. It could even hunt small vertebrates, such as lizards. The most striking thing is the evolution of its skeleton, especially the skull. We can observe a scaly bone located in the temporomandibular joint area. This bone not only affected the animal's ability to hunt and feed, but also served as a place for the auditory organs with a tympanic cavity. Now let's move to the ocean, where significant advances in marine life were also unfolding. It's an amazing place, if your heart is in the right place. The creatures that inhabit these sea depths were far from calm. About 140 million years ago, the climate was milder and the water temperature had increased. Warmer water meant an abundance of marine microorganisms, especially plankton. Plankton is a real blessing for the marine environment, since all marine organisms benefit from this abundance directly or indirectly. These microorganisms thrived at all levels and in various forms, from echinoderms like starfish and sea urchins, to sponges and invertebrates such as corals, crustaceans, and mollusks. Around 100 million years ago, fish and other aquatic animals, especially sea turtles, appeared. Like other marine reptiles, they could reach gigantic sizes during the Upper Cretaceous period. Some species reached a length of 3 meters, and the wingspan was 5 meters. There were also some fairly large specimens similar to modern leatherback turtles. 2 families of these turtles already existed at that time: Hacylondia and Dimcalid. Cretaceous turtles also included the loggerhead turtle, and of course, fish have always been a numerous species on the planet. Some rays and sharks competed with large predatory reptiles, including giant sharks such as the almost 5-meter Oran tow truck and the nearly 6-meter Ludus. Approximately 100 million years ago, we could have seen giants like Letus, whose length exceeded 15 meters. This representative of the marine world fed on plankton, which indicates that a carnivorous diet was not a prerequisite for achieving such impressive dimensions. However, even in those days, other sea predators were no less ferocious. Encotus, for example, lived in Northern America and the Mediterranean, hunting cephalopods and other small fish thanks to their long, serrated jaws. We've talked a lot about the marine reptiles of the Triassic period, as well as their widespread distribution in the Jurassic and Cretaceous periods, but not everything was smooth. Remember, we already mentioned the fragility and decline of some of these species. In particular, the Cretaceous period was their death sentence. But which marine species were we referring to? The ichthyosaurs. Although scientists have put forward several hypotheses about their disappearance, it remains a mystery. While ichthyosaurs were not as numerous as others, they made full use of their environment. Plesiosaurs could move freely and mosasaurs could quickly spread, becoming new, terrifying creatures. Plesiosaurs had a hard body and 4 fins. They could dive into the pools were the same size, and their huge, elongated neck made them truly terrifying. The little turtles looked like a cross between a snake and a turtle, but among them to one amazing creature known as Elasmosaurus, which is rightfully considered the champion in neck length. This creature had 70 to 72 vertebrae, which made it truly incredible. I find it almost impossible to imagine how a creature with a wingspan of 16 meters could ever fly. But Quetzalcoatl, the largest of the therozoid birds, managed it. I try to picture it. The size of 3 cars in a row or a bus with 4 axles, and then imagine that thing taking flight. On land, this reptile walked on all 4s. Traces confirm it. It seems it could take off from the ground by jumping, then fly with repeated wing beats. Scientists still debate its diet, though. The fossils were found on land, not near the sea. Perhaps it ate fish or scavenged for freshwater vertebrates. A mixed diet of prey and carcasses is also possible. These discoveries lead us to another fascinating family: the first dinosaurs capable of flight. I'm thinking of Archaeopteryx, the feathered dinosaur. Recently, another feathered dinosaur was discovered, one that looked remarkably like a bird. This specimen had wing proportions comparable to modern birds, but research continues, and definitive conclusions are still elusive. Paleobiology is a field that sparks controversy. Questions about how these creatures flew or how they lived remain only partially understood. Some believe we know very little about their lifestyles. It's possible they lived in trees and ate insects. Insects have relatively weak muscle strength compared to our modern birds. Perhaps these dinosaurs also fed on dead fish or worms. Among the more famous examples of feathered dinosaurs, there's Iberomazornis, discovered in Spain, and Confuciusornis. The latter was relatively small, about 50 cm in length and weighing no more than 1 kilos. Paradoxically, in some respects, Confuciusornis seems more developed than Archaeopteryx, which is considered more primitive. In its skeleton, you can see the pygostyle, a unique fusion of several tail vertebrae and the sternum. These elements are necessary for attaching important muscles used during flight. Another feature is the presence of large cartilage that could attach to the pectoral muscles. On the other hand, it retains large claws on its forelimbs, and its skull is less developed than that of Archaeopteryx. Unfortunately, most animals we know about, with the exception of mammals and some bird-like dinosaurs, would disappear within a few thousand years. The Upper Cretaceous period was coming to an end, bringing with it a terrible biological crisis. 5 such mass extinctions have occurred in our planet's history. One of the most significant marked the end of the Cretaceous period and the beginning of the Paleogene. This extinction was the culmination of the Mesozoic era and preceded our modern Cenozoic era. As with other extinctions, many questions remain about the causes and circumstances. Despite the millions of years that have passed, we still can't determine the exact reasons. As our knowledge grows and new discoveries are made, hypotheses emerge, sometimes confirmed, sometimes refuted. Many reasons may be interconnected, unfolding over thousands of years. In the case of the Cretaceous extinction, There are many hypotheses and disputes about its causes. For a long time, archaeological, biological, paleontological, and geological research has focused on this. The crater left by the meteorite in Mexico, Chicxulub, is 180 kilometers in diameter. I find myself thinking about that immense impact and the darkness that followed, a darkness filled with dust, gas, and acid rain. It's a sobering thought, the blast wave sweeping away all living things for hundreds of kilometers. We are still piecing together the puzzle of what happened 65 million years ago. There are different hypotheses, of course, but many elements are starting to point toward a single theory. Perhaps it's because the crisis of that time resonates so strongly with our current challenges. Its consequences, after all, are still visible in the world around us. One possibility centers on the Deccan Traps in India, where volcanic eruptions raged for an incredibly long time, perhaps 300,000 to 1,000,000 years. Imagine the thick smoke pouring into the atmosphere, the relentless acid rain. But that might not be the whole story. Some scientists believe a massive asteroid, sovereign in size, struck the Earth around the same time. The discovery of iridium in geological layers dating back 65 million years lends weight to this theory. Iridium, you see, is rare on Earth but abundant in the universe, especially in metallic asteroids. The aftermath was truly catastrophic. Earthquakes, tsunamis, and hot debris flung into the atmosphere triggered a domino effect. Thousands of tons of these burning remnants rained down on the planet, igniting massive fires that consumed millions of hectares of vegetation. For many animals unable to escape, it must have seemed like the end. But the long-term consequences for flora and fauna were even more devastating. The dust that choked the atmosphere blocked sunlight, preventing plants from photosynthesizing. Most couldn't adapt. Acid rain, caused by gases released during the impact and eruptions, further devastated plant life. Soon, large herbivores were in danger, a stark reminder of how interconnected the food chain truly is. The decline of herbivores led to a shortage of food for carnivores, a true disaster. Some animals scavenged for a time, but those resources dwindled and death became a grim reality for many. Even marine life wasn't safe, as acid rain contaminated the oceans. Plankton, the foundation of the marine food web, suffered greatly, leading to the gradual disappearance of countless species, both vegetarian and carnivorous. It's estimated that thousands of species on land, in the sea, and in the sky vanished during this time. Millennia proved powerless against this massive catastrophe. The new climatic and geological conditions completely disrupted the food chain, leaving many species unable to find enough food and water to survive. Yet, amidst this devastation, a group of creatures managed to persevere, mammals. Some, of course, perished, but others found a way. Small mammals already adapted to living in darkness were less affected by the lack of sunlight. They could navigate and move even in the dim conditions. While light diminished, warmth remained a challenge. But mammals, being able to generate and conserve their own heat, possessed a crucial advantage. Their small size and modest food requirements also played a role in their survival. They could more easily find enough resources compared to larger animals with greater energy demands. And And so, while the Mesozoic era is often called the Age of Dinosaurs, the Cenozoic era became known as the Age of Mammals. Among the survivors were crocodiles, turtles, lizards, snakes, and certain families of mammals and birds. The mammals that weathered the crisis became a rare and vital species, poised to shape the new era that was dawning. But that, as they say, is a story for another time.